Nothing beats. This video, we're going to do a little bit of a refresher on polar curves, because you could probably guess what we want to do. We want to find derivatives of polar curves. Let's go. All right. So the first thing we want to do is just compare the rectangular coordinate system with the polar coordinate system, because they are different coordinate systems. So first, the rectangular coordinate system, and this is the one that we're used to seeing thus far. Pretty much everything we've done so far in these Calculus 1 videos is focusing on functions that live, if you will, in the rectangular coordinate system. And so what does that mean? Well, it just means, the system, the Cartesian system that we're used to. And that is, to plot a point, some point, say, x comma y, what do? You start at the origin, 0, 0. You move horizontally x units, either to the left or right, from that place, depending on the sign of x. And then from there, you move vertically y units to get to the location x comma y. And of course, which quadrant you are in all depends on what the signs of x and y are. So, things like this, right? Here is, it's a little silly to think about at this point, but we got to say it, right? You start at the origin, 0, 0. You move x units left to right. You move y units vertically from there. And of course, when we draw such a point, it forms a rectangular grid, hence why we call it the rectangular coordinate system. And then just on the right over here is just a picture showing like, hey, here's a function in the rectangular coordinate system, right? We've been dealing with a lot of these functions so far. But the rectangular coordinate system isn't, of course, the only coordinate system. There are many others that we can use. And depending on the situation in which we're dealing with, it may be more beneficial to use one coordinate system over the other. That's why we talk about this polar coordinate system here. So the polar coordinate system, remember, we defined an ordered pair in the plane by this ordered pair right here at the bottom, r comma theta. That's our ordered pairs in the polar plane, as we're going to say. And to get to this location in the plane, let's call the point P r comma theta, what do? Well, we don't go left and right from the origin and up and down anymore, right? That's the rectangular coordinate system. Rather, what we do is we start on the positive horizontal axis. And then what we do is we rotate counterclockwise theta units of angular measure. And when we're rotating counterclockwise here, that is the same as saying that theta is a positive value. So just kind of think back to like trigonometry, starting from the positive horizontal axis and rotating some angular measure theta. Counterclockwise is the positive orientation and clockwise is the negative orientation. So that's the first thing we do. And then once we rotate that amount of angular measure, then we move a distance of r units here from the pole, as we say. So the pole is just still this ordered pair 0, 0 in the polar plane. But now it means different things, right? Instead, it means that your angle is 0 and your distance from the pole is 0. So after you do that, then you arrive at our destination, point P, r comma theta. So got a little picture here to remind us of that. So here we go. Here is an example of a point in the polar world. Here's that point we're talking about, right? Some point r comma theta. And what do? Right down here, we moved an angular measurement of theta. So it could be degrees, it could be radians, depending on the situation. And we're starting, of course, on the positive horizontal axis here. And then from there, we move that angular measure theta. And then we draw this distance r here, right? That's the distance from the pole. So our pole is still right here, as we say, 0, 0. and we move a distance of r units from there to obtain the location, the point P, in the polar plane. So clearly we're getting to this location in a different way. It's kind of like a straight shot, right? We're going to start at one location, in this case 0, 0, and we're going to, like, say, walk straight to this location P, whereas in the rectangular world we're moving left, right, up, or down. So another thing to remember is that the values of r and theta don't need to be positive, right? They can be negative. And I mentioned what happened with theta being negative a moment ago in this video. If theta is negative, that just means you rotate clockwise rather than counterclockwise. Now, what happens if r is negative? Just as a reminder, if r is negative down here, then to find the location of this point P, r comma theta, is just that r is a negative value. We first go to the location absolute value of r comma theta, so that makes the first coordinate positive now, and then we go to that location, and from there we rotate 180 degrees or pi radians to get to our location of P equal to r comma theta. So here's a picture depicting that. So as you can see, my point is down here, right down here, right there. But remember that we're assuming r is negative. So maybe like this point is, just make something up, maybe -3, comma, I don't know, 45 degrees, for instance. Then this point over here in the top right would be the location 345 degrees, right? Because my r is now positive because I took the absolute value of it. And so we first go to that location, and from there, as we can see, we've rotated pi radians or 180 degrees from that location to obtain our point down here in the bottom left, which is the actual location at the point -3, 45 degrees. And so that's the kind of process we have to go through when we are dealing with an r coordinate that is a negative value. So it's just all, again, this is all just a refresher so we can get to what we want to really talk to, and that's the slopes of polar curves. Now, remember, there's this relationship between the locations. If we have a point x comma y in rectangular coordinates and a point r comma theta in polar coordinates, then they will literally be at the exact same location in the plane through the conversion. X is r cosine theta and y is r sine theta. And this is all just stemming, of course, from the concept of trigonometry and how we go back and forth between those two different coordinate systems. Also true, if you recall, is the relationship that the tangent of theta is the ratio of y divided by x here, assuming y is the output variable. And so you just think of this picture right here, right? This picture should look familiar from like a trigonometry standpoint. Here's my point, r comma theta, in the polar world. And then we have this angle theta right here, right? So then how do we figure out what the sine of the theta is, for instance? Well, of course, the sine of this theta is just going to be the opposite of this triangle, this right triangle here, right? We do have the right triangle in this picture. So that's the opposite y over r, and hence we get that y is r times sine theta. And then the cosine of this angle theta is the adjacent side, x over r. And that tells us that, of course, x is r cosine theta. And so if we wanted to find the equivalent location, this point right here, P, in rectangular coordinates x comma y, we would use those conversions. And then, of course, we also stated a moment ago, tangent of this angle theta is the opposite side, y, over the adjacent side, x. So there's these relationships that we have between the polar coordinates and the rectangular coordinates. And so sometimes we do need to convert back and forth. So again, it's just a reminder here. Now, what about the polar curves? Because that's what we're really trying to get into. We just set up like, how do we deal with the polar coordinates? But of course, we can have curves in the polar plane. Suppose that you have a function, r is a function of theta here. and that is in the polar coordinates. Then we can plot the graph of this function in the polar plane just like we would do with a graph in a rectangular plane, and that is by plotting all of the ordered pairs that satisfy the given rule within the function. So when we do such a thing, we call that a polar curve. It's just a curve in the polar plane in polar coordinates. And these curves are not necessarily going to quote-unquote pass a vertical line test, and that we don't care about because we're no longer in the rectangular coordinate system, so it's no longer applicable. So for instance, just to see an example here, suppose we have the function right here, r is equal to f of theta, let's say, is 4 cosine of 2 theta. Now one thing to take note of is r is usually our output variable in the polar world, but we use it as the first coordinate in our points, and that's kind of counterintuitive to how we use the rectangular coordinate system, in which the output variable y is usually the second coordinate. So just take note of that. But let's try to just refresh our memory of these polar curves by looking at this particular function here. R is equal to 4 cosine of 2 theta. And so first thing, let's just look at a variety of points on the graph here. So these two tables are showing us a whole variety of points. So I just picked increments of theta values of pi's over 12s. And so you can see in this first table here, I'm going through all these angles with increments pi over 12s from 0 to pi over 2. And then in the second table over here, I'm going through all of the theta input variable values from 7 pi over 12 to pi. So it's kind of like half a revolution on the unit circle, if you will. And we see a bunch of ordered pairs, right, given to us. So like, for instance, 0, 4. If I plug in 0 into my function right above, I get 4 cosine of 0, which is 4. So then theta would be 0 and r would be 4. And really what you can think of that as is the ordered pair 4, 0 in polar coordinates. And you just go through these. You can verify them by just plugging them in. And, you know, it is a little tedious at first to plot this point by point, but we just want to make sure we understand that we can do this the same way we do with explicitly defined functions. It's just that now to get to these points, we get to them in the polar way, not the rectangular way when we plot them. So you see a bunch of different ordered pairs here, right? And in fact, if you take all those ordered pairs and you plot them, we start seeing a picture like this. Like, so for instance, this point right there, there's the point 4, 0. And so our tick marks here, like here is r is 1, here is r is 2, r is 3, r is 4, right? This grid, by the way, is a polar grid, a bunch of circles depicting the different radii that are associated with the outputs here. And so there's that point 4, 0. And so what else? Like, how about this point right there? That is at an angle of pi over 6, right? From the positive horizontal axis. And where are we? We're at a radius of 2 units away. 1, 2. Boom. So that point would literally be r is 2, and the angle is pi over 6. And so on and so on, right? We see a whole bunch of different points here. And so you think maybe as we go through these points, seems to be that that first part is doing something like that, right? And then we'd have to go through the table of values to see what happens next. And in fact, if we did this at least all the way from the theta is equal to 0 to theta is 2 pi, we can keep plotting more and more points. And what we would get is a graph that looks like this, like a flower petals, if you will. And so this is the graph of r is equal to 4 cosine of 2 theta in the polar world. And we can get these types of graphs. It's quite pretty, as you can see. And, you know, it is what it is. We're going to deal with these graphs. And in specific, just pick a point here. Like maybe let's pick that point right there. And what if we asked ourselves, what is the slope of this polar curve at that particular point? Well, we'd have to find the slope of the tangent line at that location. And that's exactly what we want to do. And so this video was supposed to help us just kind of quickly get back up to speed dealing with polar curves, because it's not something that we deal with quite often up to this point. And so hopefully it's a little bit of a refresher that now leads us to the next video, in which we will look at how to figure out what the slopes of these polar curves actually are. So that's it for this video, refresher on polar coordinates and polar curves. Next video, slopes of polar curves. And until then, you know what it is. It's Math and Beats. I'm out of here.